Welcome back to the deep dive. Today we are tearing into the very foundation of modern AI. We're talking about the revolutionary architecture known as the transformer model. It's the engine driving, well, every major large language model you interact with.
That's right. I mean, whether you're drafting an email with an AI or, generating code, the quality of that output rests pretty much entirely on one core mechanic, and that is the attention mechanism.
Right, and from what we've seen in the literature, attention is often the most confusing part for people. So our mission today is to make that whole mechanism feel concrete, to really demystify the math and connect it to how a model actually, reads and understands context.
And we have to start with the foundational text. The whole deep learning world really changed in 2017. A paper came out with this really defiant title, Attention is All You Need.
I love that title.
It's great. And it proposed just throwing out the previous titans of this field recurrent neural networks, RNNs, and even the masters of image processing, the CNNs. They just argued that attention alone could do the job and do it better.
So let's just set the stage for you. The model's ultimate goal is simple on the surface. It takes some input text, it breaks it down to these little pieces called tokens.
Which can be words or sometimes parts of words.
Exactly. And then it just tries to predict the very next token. But the absolute first step is to turn each of those tokens into a vector.
Yes, a long list of numbers.
Yeah.
And that vector is called its embedding. You should really visualize this not just as like a spreadsheet of numbers, but as a point in this vast high-dimensional space. The real genius here is that directions in the space correspond to actual semantic meaning.
Can you give us an example of what that looks like, that encoding of meaning?
Yeah, so a classic one is if you take the embedding for a word like king, and you subtract the vector for man, and then you add the vector for woman, the point you land on in that space is incredibly close to the vector for queen.
Wow.
So the relationships, gender, singular versus plural, they're literally encoded as, geometric directions. It's meaning, but quantified.
That's incredibly powerful. But here's where the problem starts, and where attention becomes so necessary. That initial embedding is completely context-free.
Precisely. It's just a static lookup table. It's like a dictionary definition that doesn't care at all what sentence the word is in.
Okay, let's use that classic example from the sources. The word mole.
Yeah.
You could see it in American shrew mole, which is an animal.
Right, or 1 mole of carbon dioxide, a chemistry unit.
Or take a biopsy of the mole, which is a skin feature.
And in that initial phase, before any real processing happens, the vector for mole is identical in all 3 sentences. The model has absolutely no way of telling the difference between the animal, the unit, or the skin feature. That generic vector just holds the sort of blended average meaning of all possible moles.
And obviously, if the model wants to predict the next word, say, after 1 mole of carbon dioxide, it has to know we're talking about chemistry, not, dermatology.
Exactly, and
Yeah.
that's the job of the attention mechanism. It has to calculate the precise change, the exact vector. It needs to add to that generic mole vector to push it towards the chemistry mole, meaning it has to correlate it with carbon dioxide and ignore things like shrew or biopsy.
And this has to happen even if the key context, like the word Eiffel, when you're talking about a tower, is separated by, 10 or 20 other words. The complexity is just immense. The final vector for the very last word has to have encoded all the relevant information from the whole context.
I mean, think about it. If you feed a model an entire mystery novel and the last sentence is, therefore the murderer was, that final vector for the word was can't just look at its neighbors. It has to have pulled in the who, what, where from thousands of words earlier to have any chance of predicting the culprit's name. And that entire heavy lift is done by a surprisingly elegant series of matrix multiplications.
Okay, let's break that down. Let's get into how that actually happens inside a single attention head. We can use a simple analogy. A noun getting its context from adjectives, like in the phrase, fluffy blue creature.
Right. So to do this, every single word in the sequence takes on 3 roles at the same time. It's a seeker, it's an identifier, and it's a supplier. And these roles are played by 3 new vectors we create: the query, the key, and the value. You get all 3 by multiplying the word's initial embedding by 3 different learned matrices, WQ$ and $.
Okay, let's start with the seeker, the word that actually needs the context.
That would be the query Q vector. You can think of it as the question a word asks all the other words. So for our noun creature, the query is basically asking, are there any descriptive words around here that apply to me? It's asking for information.
And how did the other words like fluffy and blue kind of advertise what information they have.
That's the key, K vector. The key is like an identity tag. It represents a potential answer. And the whole system is trained so that keys and queries that have a relevant relationship will align, they'll match mathematically. So the keys for fluffy and blue are specifically tuned to match up with the query that comes from creature.
Okay, so we have a question, the query, and a bunch of possible answers, the keys. How does the model measure that match?
With the dot product, it's a really efficient mathematical operation. We calculate the dot product between the query of our target word, creature, and the key of every single other word in the sentence. This gives you a raw relevance score. A high score means highly relevant.
And since this happens for every possible word pair, you end up with this huge grid of scores. It's like an internal map of how relevant every word is to every other word.
Exactly, but those raw scores, they're not quite usable yet. We need to turn them into weights, like a probability distribution. And that brings us to normalization.
Hold on, before we get to the final weights, you mentioned a scaling step. Why is that necessary? Can't we just use the dot products as they are?
That's a great question. You have to remember these query and key vectors have been projected down from, say, a 12,000 dimension embedding space to maybe just 128 dimensions. And when you calculate dot products in high dimensional spaces, the scores can get really, really big. They can have huge variance. And that can make the next step, softmax, very unstable. It can just wash out all the smaller but still important relationships.
So really big numbers are just bad for stability.
They are. So to fix it, they just divide all the raw scores by the square root of the dimension of that key query space. That scaling step brings everything back into a nice stable range.
That's such an elegant little fix for what sounds like a huge problem.
Yeah.
Okay, so what's the next normalization step?
The second step is softmax. We apply the softmax function to the scaled scores for each word, kind of column by column. And this transforms those scores into what we call the attention pattern. It's a grid of weights, all between 0 and 1. And for each word, all the weights it's paying out to other words sum up to 1.
So that final pattern tells you the exact percentage of attention each word should pay to every other word.
Right. And for a model like GPT, which is autoregressive, it only predicts the future based on the past, we have a constraint during training. We can't let a word get information from words that come after it.
That's where you have to prevent the model from cheating, right? With masking.
Exactly. In what's called masked self-attention, the model looks for those illegal connections, a later word trying to influence an earlier one. Before softmax is applied, the scores for those connections are just set to negative infinity. And because softmax involves an exponential, a huge negative number just gets squashed down to 0. So those connections are effectively erased.
Okay, so now we know how much attention to pay. But we still need to know what information is actually being sent. That's the third vector, right?
It's the value v vector. So unlike the query and key, which were in that smaller space for efficiency, the value vector is usually back in the original high-dimensional embedding space. It's the actual payload, the semantic information that a word has to offer.
And now we get to the final combination. We take the weights from the attention pattern and apply them to the payloads, the value vectors.
Yep. For our word creature, we take the value vector of fluffy, the value vector of blue, and all the others, and we do a weighted sum. The weights for useless words like the will be near 0, so their value vectors contribute almost nothing.
But the high weight words, fluffy and blue, they contribute their entire semantic payload.
Exactly. The sum of all that is a new vector, let's call it delta E, which is the context injection. That change is then added to the original context-free embedding of creature, and suddenly you have a new, refined vector that knows it's a fluffy blue creature, not just any old creature.
Okay, so that explains one type of relationship, like adjective-noun. But language is way more complex. You need to track who the subject is, where the action is, what the tone is. A single attention head can't do all of that.
It can't. It can only learn to specialize in one thing. And that's why we have multi-head attention. The full attention block isn't just one of these operations. It runs many of them completely in parallel. Each head has its own totally independent set of learned matrices, its own WQ-dullers and Teller-Busies.
So one head might learn to track adjectives, while another one is specializing in, say, pronoun resolution, like tracking that the word it from 3 sentences ago actually refers to the Constitution.
That's a perfect example. You need a head for syntax, a head for semantics, maybe one that's good with numerical facts, another for sentiment. By running them all at once, the model can jointly attend to information from all these different angles simultaneously.
And the scale of this is just wild. If you look at a model like GPT-3, we're talking about 96 attention heads all running inside a single block.
And the way they're combined is surprisingly simple. Each of those 96 heads produces its own proposed update vector. All 96 of those proposed changes are just combined and then linearly transformed before being added to the original embedding. And that sum becomes the new, fully context-rich vector that gets passed on to the next layer of the network.
And the scale just keeps going. That entire multi-head attention block is just one layer. In GPT-3, that whole block is repeated 96 times in 96 distinct layers.
It's staggering. If you add up just the parameters for attention across the entire network, it's almost 58 billion parameters just for the attention heads. So while we call attention the secret sauce, it's really this massive, multifaceted operation that makes up about a third of the whole model.
Which brings us to why this was so revolutionary. I mean, the transformer didn't just improve things a little bit, it fundamentally changed the game. Why was the decision to rely entirely on self-attention so effective?
Well, it solved the biggest bottleneck in deep learning at the time, which was sequential computation. The older models, the RNNs, had to process a sentence one token at a time. If you had a 1,000-word sentence, that's 1,000 dependent steps.
You couldn't parallelize it.
Yeah.
You had to wait for step 999 to finish before you could even start on step 1,000.
Exactly. That's the bottleneck. The complexity scaled linearly, what we call low sequential operations. But the self-attention mechanism connects every word to every other word instantly.
Right, because calculating all those dot products is just matrix multiplication, which can all happen at the same time.
Yes. Self-attention has a constant number of sequential operations, what we call O-hour. That was the fundamental difference. It allowed engineers to finally unleash the massive parallel power of modern GPUs. Suddenly, you could just throw more compute at the problem and get these huge qualitative jumps in performance.
It's really hard to overstate how big a deal that was in 2017. The results in the paper show it immediately. The transformer got state-of-the-art translation scores, beating all the previous models.
And the cost savings were just unbelievable. Their big model got that performance after training for just 3.5 days on 8 GPUs. I mean, other models took weeks, sometimes months. Parallelization just made training at scale suddenly feasible.
Now, attention is obviously the star of the show, but it doesn't work completely alone. The base transformer has these stacks of layers, and inside each layer, after the multi-head attention, there's another key component, the position-wise feed-forward network, the FFN.
The FFN is absolutely essential because at its core, the attention operation is linear. It's just dot products and weighted sums. If you only stacked attention blocks on top of each other, the whole network could just collapse into one big linear transformation, which would really limit what it can learn.
So the FFN is what provides the necessary nonlinearity.
Yes. The FFN is applied to each position separately. It's basically two linear transformations with a nonlinear activation function like ReLU in between, and that's what introduces the complexity and depth the model needs to really learn features from that new contextualized embedding.
Okay, there is one last just brilliant piece of engineering we have to cover. If the model is processing all the tokens at the same time, in parallel, it completely loses any sense of word order. It doesn't know dog bites man from man bites dog.
That's the paradox of parallelization, right? By ditching the sequential part, you just have a bag of words.
Yeah.
You know what's in there, but not the structure, so you have to artificially put that information back in.
And that's where positional encodings come in.
Correct. These are just vectors made from sine and cosine waves of different frequencies, and they're just added directly to the input embeddings right at the very beginning. This gives every single position in the sequence a unique signature, so the model can learn the structure even while it's processing everything at once. It's how it knows dog is in position 1 and man is in position 3.
So this deep dive has taken us all the way from these static context-free vectors to this massive scale of 58 billion parameters. You should now understand that attention is this mechanism for taking a word's basic meaning and just progressively refining it, layer after layer, building up from simple grammar to abstract ideas like tone or sentiment.
Yeah, and the success isn't just about speed. It's about the capacity this gives the model to learn these incredibly complex, long-range dependencies in language. The further down the network the embedding goes, the more nuanced it becomes because it's taking in meaning from its equally complex and nuanced surroundings.
And to leave you with one final provocative thought. One of the most fascinating findings from analyzing these models is just how interpretable the attention mechanism can be. When researchers actually look at the learned weights, they find that specific attention heads seem to specialize in very clear linguistic tasks.
Yeah. The sources show some heads that are clearly learning anaphora resolution. They're literally drawing a connection from a pronoun like it all the way back to the noun it modifies. Other heads get good at subject-verb agreement. So what this means is, as you read or interact with AI, remember that the attention mechanism is sometimes literally showing you its thought process. It's revealing the grammatical and semantic structure it decided to focus on.
We hope that gives you a much clearer picture of the machine behind the magic. We'll see you next time for the next deep dive.